Hi, my name is John Messenger, and behind me here is a Bridgeport Series 1 Boss 6 CNC milling machine that I have upgraded with the Centroid CNC package from Ajax CNC. I want to give you a little bit of history on this machine. I picked this up from a gentleman who was working on doing the upgrade. He purchased it with the intention of doing the upgrade, and he had purchased the kit from Ajax. And then I don't know what happened. He either ran out of time or money or space or had to move something. But he had to get rid of the machine. He had just barely actually started the project when he listed it, and I was able to make some horse trading and pick this up from him. So I kind of got the system in pieces. Some of it had already been gutted and taken apart. Some of it, the screws had been pulled out, things had been lost, whatever. It always makes it fun when you pick up somebody else's project. But it didn't come with a construction manual for the all-in-one DC installation. Well, I went to the all-in-one DC site from Ajax, and I thought I downloaded the correct PDF, but apparently the version I have is newer than the version that the software, or the PDF that I downloaded. So I was struggling with it, having some difficulties with it, and finally I was able to get hold of the people there at Ajax, and they went ahead and pointed me in the right direction, got me the right software and the correct manuals to do the install. But I'm a guy that likes to go to YouTube and learn things. This is one of the most wonderful tools that we have. And so I thought, well, you know what? I think I'm going to go ahead and make a video of my retrofit of my old Boss 6 machine, especially the focusing on the board. And hopefully that will help somebody else down the road. You can see how I've done it, what I've wired in, where all the wires go, how they function. And we'll be helping you with that. So we're going to take a step back in time now, and we're going to go back to the process of installing and building this machine. So stay tuned. We'll get that done right now. Okay. Due to some unavoidable circumstances, I inadvertently deleted the first several minutes of this segment. And this is basically, it was just the overview of the board and the layout of the board. Well, I've already, as you can see, done the install. It's in the cabinet. And I really didn't want to pull it all out again just so that I can shoot the first 5 minutes of this video over again. Excuse me, I got a bit of a cold today. So what I'm going to do is I'm kind of leaving it in the cabinet, and I'm going to give you an overview of the layout of the board. There are some obstacles in the way here. There's this rail here that kind of blocks the view of some of the elements in the cabinet, but you can see parts of them. It doesn't really matter the layout, how you do it. All that really matters is that all these elements are in here. This is your all-in-one DC board here. This is the capacitor with bridge rectifier on top of it here. There is a switching power supply right here. It comes with your kit. This is provided by Ajax CNC. There is a 24 volt AC power supply right here. Again, this beam is kind of blocking it out of the way. Down here, there are 3 contactors that have been mounted to a DIN rail. There are the terminal blocks here, and I have put a Chinese inverter here. I've actually had a great deal of luck with these Chinese inverters, and we'll kind of go through that a little bit when I go through the setup and tell you how I have it wired to make it all function. It's important to note that for the bench test of the operation, all you need are 110 volts in. Now I've got 220 volts in here because I'm running a 220 volt spindle motor. But for the board portion of it, you only need to pull off the 110 leg and your common. You will run a wire from that into the power input on your switching power supply. You will run another bridge from that leg into your 24 volt AC transformer. You will run another leg of that into the input side here of the bridge rectifier, which sits on top of your capacitor. And that is all you need for the preliminary testing of this board. Once you get that hooked up, wired in, bring your PC, your switching power supply voltages here. They are basically the same as an ATX power supply for colors. That means that your red is 5 volts, your yellow is 12 volts positive, black is common, blue is 12 volt negative. You'll bring them into, down, route them through your channels, around in here, up in here. I brought mine into right here. By keeping my my wire connections correct, I could then use the input power supply plug from Ajax. They are wired the same way, so that the colors are 12 volt red, or 12 volt yellow, 5 volt red, 12 volt negative blue, and common is black. So that you just go yellow to yellow, red to red, blue to blue, black to black. That keeps that very simple and satisfying. Also, and that's all you will need in order to test this system. And we'll go ahead and go through the bench test system now. And we will go ahead and talk about some of the other things later on as we get to them. And I'm going to make some assumptions here. I'm going to assume that you know what a computer looks like and how to turn one off and on. I'm also going to assume that you know how to install software, so I'm not going to show you how to install software. I will caution you, however, it is imperative that you follow the instructions in the manual step by step, precisely as they're laid out. If you do this, you will have no difficulties. If you do not do this, you will have a lot of difficulties. So, depending upon the amount of difficulties you wish to have, now I'm an experienced guy, I've been working with software and computers for a long time. I've built hobby CNC machines in my shop for the last 12 years. I mean, this is not my first rodeo. However, read and follow those instructions step by step. They're very precise and they're very accurate. And if you do that, everything will install properly and your board will come up and function properly and we can move on. So now I'm going to go ahead and cut back to the original segment of the video where I start showing you the bench testing system. And you can see that the LED number 1 is blinking forward. That's because right now the blinking LEDs will always mean an error, by the way. So a blinking number 4, if you look in your manual, tells you that there are no home and limit switches enabled on this machine. Which, as I said before, we know that is correct because we don't have anything on this machine other than an Ethernet cable and power. Right here it says limit switch defeats. There is a series of dip switches right here on this panel board. On the lower 6, the 6 closest to the Ethernet port, are the ones that we're going to, right now we're going to pull them up. And as we pull them up, it will defeat the limit switches and lie to the system and tell it that there are home and limit switches enabled on this machine. And as you can see there, it's switched now to a solid number 1 on the LEDs. And then we're going to navigate to the control configuration. So we're going to go to F1, setup. We're going to go to F3, which is configured. We're going to enter the password there, which is 137, and hit enter. You are now in the configuration menu. From here, we need to configure the control. Go to Control F1, and you'll see this screen. Now, my machine is set up for inches, so I'm going to leave it at inches. Let me get my pointer here. Inches. Use your arrow keys to navigate through these screens. The max spindle speed range at the moment, I'm going to leave it at 3,000. The minimum is 0. I'm going to leave that there. Right now it is set up to machine home at power, what it's going to do. And right now, excuse me, it's set to go to home switch. Using the space bar, we can change these options. You'll notice off to the left-hand side, or the right-hand side of it, you'll see these are the options there. Job, home switch, or reference mark. Since we don't have any home or limit switches engaged yet, we're going to change our option to job, which means That's power. The machine is going to ask us to jog to the position that we want to call home, and then call it home. Well, if you're just doing the bench test, you're not going to have any motor or everything hooked up, so you can do that at any point, and that's why we set it this way. PLC type is standard. If you have a jog panel, go ahead and install it here as either jog board legacy or offline. Jog board is what you do if you have the jog panel. We're going to leave it as offline since we don't have anything hooked up to it at the moment. And is that jog panel required? Obviously, since we don't have one, the answer is no. We're going to leave that. We're going to press F10 to save that screen. Now, in order for that to take effect, we need to restart the entire system. So we're going to go ahead and escape. Escape will always take you out to the main menus. Just keep pressing it until it doesn't change anymore, then you know you're at the main menu. We can press F10 to shut down, F2 to power off. That will actually power and recycle the machine. We'll need to shut off the power to the board as well. You can't just leave it running, it has to reset it both at the same time. When you cycle that, be sure that you power off the board and the computer for about 30 seconds, let all the power die from it, and then re-energize the board. This way everything will take place. If it did not do it properly, you'll get a software limit fault or a software fault here on the screen. And it will tell you that the computer was repowered, but the board was not repowered, and it knows the difference. So make sure that you give it a full 30 seconds and then restart it. At this point, we're going to need to go ahead and disable some of the error checking on the board. Since we don't have home, limit, lube pump, spindle, anything hooked up to it, we just want to check to make sure everything is functioning. We do that by coming from this screen right here, and we're going to hit alternate I on your keyboard. When you press alternate I, it brings up your inputs and outputs, memory and stages screen. It should be hovering over number 1, which should be red at the moment, and it should say access 1 minus limit OK. So it's red, which means it's not OK, but that's what it's checking for, is whether it's OK. In order for us to enable these, without doing anything other than software only, we have to hit Control Alternate I while we're hovering over the one we want to change. So if I change that to Control Alternate I, it goes green. Using our arrow keys again to navigate, we do that for all of the home and limit switches. Which there are 6 of, as I remember, as I told you, I don't know if I told you or not, but this system requires a limit switch and a home switch for each axis. So it requires 2 separate individual signals for each axis. So that's why there are 6 of them here lined up. Now, also, we have to do 9 and 10 and 11. Well, 9 and 10, well, 9 is for your lube pump error. The float in your lube pump, when it goes down to a certain point and closes, it will send an error signal 405 to the system telling you that your lube pump is needing to be checked. So we're going to go ahead and enable that, since we don't have that hooked up either. Control Alternate I. The next one is spindle fault. And if you look down here, right here, where it says, it tells you what you're hovering over. Spindle, inverter, OK. So since we don't have our spindle hooked up yet, we're going to need to tell it it is hooked up and it's OK. Alternate I, turn it green. And since we don't have an emergency switch yet, we're going to go ahead and go over and tell it that the emergency switch is OK. Now you may have heard when it did that, I don't know if you did or not, but when it did that, it sent a signal to a relay on that board. That relay is the no fault relay on the board. It clicked on. When it clicked on, over here on number 1 on outputs, that is the relay for that. So It says that everything was okay in a functioning state. It went ahead and tripped the relay and sent a signal, power signal to the no fault signal. What number on output is your first one here on your all-in-one DC board. And it is the no fault switch. It's a relay. All of these are relays. This is the first relay. If there are no faults found in the input side of your system, then it will send a signal to the board telling it to close this relay because there are no faults. So everything is a go to operate. So to get out of this screen, the only way out of this screen, this little section of the screen here, by the way, is to hit alternate I. Escape does not work here. So in order to shut this off, you hit alternate I. The reason you want to do that, by the way, the reason I'm sure that they did that was so that you could continue to function the machine, and escape would go back and forth through some various menus and check and watch your limits and home switches and all your inputs and outputs and still keep that screen up here. So it does not escape. You have to hit alternate I in order to get out. Now the E switch is wired like this. The people at Ajax recommend that you use a double pole single throw switch. I don't have a double pole single throw switch. I have a single pole single throw switch, and it's an Allen Bradley. Picked it up off of eBay some time ago, and I like it because it's illuminated. It looks cool. Okay, I know that's not important, but you know, dude, it's their shop, right? It's got to look cool. So I wired my emergency switch this way, and I'll show you how, and then I'll tell you what the Ajax recommends for theirs. I have pulled a 12-volt line off of our switching power supply from this terminal block, the yellow wire, and I brought it around into the one side of my E-switch. I then come off that E-switch and go out the other side and come back to here. And I come up to here. This is common in 9 through 12. I run a jumper wire from that into common in 5 through 8, and then I run another jump wire from that into common in 1 through 4. I believe they call this syncing the system. So now all the hots are actually in the common. So I'm actually running 12 volt positive through that system, sending a signal saying that all those now have power. In order for this to function, I need to pull out the E-stop switch. I have taken 24 volts in from our transformer, brought it into the no-fault common relay, brought it out of the no-fault common relay, and back into the bottom layer of the switch or the relay here, the primary contactor. Then the other side of it here goes back into the other output of the 24 volt transformer, so we have a completed circuit. So, as you'll now notice, this is illuminated, which means that we have no faults in our system, so I can send power to my contactor. The second thing, the first thing that this contactor actually hooks to is the output side of our bridge rectifier from the on top of our capacitor. This is bringing in 110 volts here. It's putting out about 168 volts DC on this side. I've taken the red wire, brought it down through and into this side of the contactor. From this side of the contactor, it jumps out and comes back up and brings it into this VM positive here on H2 on your board. So when this emergency stop is pushed, it kills the signals to all the inputs, which means every fault is now active, and then it then sends a signal to the no fault relay. The no fault relay breaks its contact. It kills power to this relay, which in turn then would kill power to our servos. So by hitting E-stop, we've killed the powers to the servos. We've also done a couple other things. I've taken another wire and I've jumped it from the hot side here on the bottom row up to the top row here, come out this side and around and into the second contactor. So this contactor will not function if this contactor does not function. It's receiving its OK signal from here. The third thing that it does is that I brought a wire in from our spindle enable and run it through this as well. So the enable signal is also being controlled by the primary contactor. So if I hit this contactor and kill it, I kill not only the power to the servos, but I kill the power to any subsequent relays, and I kill the power to the enable switch on the spindle, so the spindle cannot operate. So with one fell swoop, we've killed, essentially stopped everything on the board, which is precisely what an e-stop should do. So at this point we can see the number one is working, the e-stop is working, and this is all set up and configured correctly. The next thing we want to do is we want to label the axes of our machine. We go to F1 setup, and then we go to configure. 137 is our password. Hit enter, bring up machine, and now we're going to go to the motor. Sensible way to do a 3-axis machine such as I have here is number 1 is X, number 2 is Y, number 3 is Z. Now you'll notice that I have motor revs, inches here. I have actually other parameters placed in here. I've already done this on my machine. When it comes stock from the factory, these should be 5, 5, and 5. I have already done the backlash testing, the compensation and all that, and I've already entered those values in here. So that's why you're seeing those in here. But they should say 5, 5, everything should be 5s in the motor column. The encoder is set to 8,000 counts per revolution. And I have backlash already compensated for here, but this will all be 0 at the time that you get it. So the big thing here is X, Y, and Z, your motor revs, and your encoder counts. After you've done that, in order to save in any menu here, you always hit F10. These are set up so you can configure them probably any way you really want to. But they're numbered 1, 2, and 3. The encoders are numbered, and the axis power supplies are numbered 1, 2, and 3. Axis 1, axis 2, axis 3. So you're not really limited to X, Y, and Z. You can do whatever you want to do. However, it's normal and standard operating procedure for everybody to actually run X, Y, and Z on a 3-axis machine. But we have to tell our software that axis 1 is X, that axis 2 is Y, that axis 3 is Z. It has to know that, so we have the ability to configure that in here. Now, we need to configure our bus assignment. And to do that, we go out one more escape. You don't have to go all the way out. And you go to F3, parameters. This brings up your parameters table. A lot of parameters in there. Most of them we don't mess with. F7 takes you to the previous table. F8 will take you to the next table. What we're looking for at this particular juncture is number 300 and up. So let's go to next table, which brings us 199, next table 299. So the next table, there it is, 3 tables over. 300, 301, and 302. These should be set to 1, 2, and 3. These are now telling the machine that the output for number 1 is here, output for number 2 is here. So your number 1 is X, number 2 is Y, number 3 is Z, which we just set up in the previous table. So those numbers correspond to these numbers. Then, if you're not using axis, you must leave these elements here as 0. Because as long as it's 0, the machine will no longer look for anything else. If there's a number in this field, then it's going to look for an encoder which is matched to that. Which is what you'll see here now in 308 and 309 and 310 are corresponding 1, 2, and 3. So this is now encoder, it goes to number 1, this encoder goes to here, and this encoder goes to here. Now you'll see 4, 5, and 6 down here. Those don't matter. You can have numbers in those fields here because they're not related to anything here. It looks here first and then looks for a corresponding number here. So once you're done with that, you also need to then go and disable the spindle axis. And we're looking for field number 35. So let's go to our previous tables. So we get back to the beginning. Number 35, we need to make sure that that is set to 0 if you do not have a spindle encoder on your machine. I don't. It's just a straight 3-axis milling machine. I don't have an encoder on that, so we're going to disable it and we're going to go to 0. When you're done, you press F10 and you save it. Now we need to disable stall detection because we still haven't hooked anything up to this machine. So if we start to do something and nothing happens, the encoder doesn't get a count back, then it's going to assume a stall has occurred and it's going to send a fault and error to the system. So in order for us to disable that ability for the machine to detect that, we need to go to F4 PID. From here, we hit Control V. It says stall detection disabled, and then a little screen over here says stall detection disabled. So let's go ahead and just save out of here. Go exit, exit, or escape, escape, escape. Brings us back to the main screen. Now yours won't look exactly like this. There'll actually be a big white block here saying this machine's not been set up yet. I've already gotten around that, so mine set looks like this. Okay, it's now time to test our spindle output controls. Since we're using a VFD, we're going to go ahead and let the machine control the speed of our spindle. Currently, I still have the old Bridgeport spindle speed control on this. I'll probably eventually go to a 1-to-1 pulley and just let the spindle have it controlled completely by the VFD. But right now, I'm going to use that eventually to tune that speed so that I'm actually, and I have a little handheld tachometer, I'll be able to set it to the proper RPMs on the software and then dial this in until the RPMs match what's on my software and hopefully get control over it that way. But the all-in-one DC board, what it uses is a voltage out signal to control your speed for your spindle. What that does is it has a 0 to 10 volts, and then it will divide it by the max and min speed. So for instance, if you're going to send on a 3000 speed spindle, you're going to send 1500 RPM, it will send out 5 volts because it's going to divide it in half. Right now we're going to test those outputs on the board by plugging our voltmeter into the spindle speed common and the spindle speed and measuring the voltage as we do that. So it's loaded up here, job name, spindle test.cnc. We're going to hit alternate S to begin. Now it's waiting for the cycle start button. What this is going to do is it will send a signal to the spindle control. We will measure it with a voltmeter, and then we will enter the values that we see. All right, we're going to hit alternate S, and it says welcome to the bench test utility. Make sure it's blah blah. We're going to hit alternate S again. Now it's sending a signal out to my machine. I am reading it at 1.8, so I'm going to type in 1.8, and I'm going to hit alternate S. It's sending another signal out, and it's looking for what I'm reading back into my machine. I'm reading 3.5, so that's what I'm going to type in, is 3.5 into my machine. It's now sending out a third signal, and it's looking for the voltage of it, and I'm reading 6 or 7.0, and then I will hit alternate S again, and then the final thing it's sending out is 3000 RPM reading, and I'm reading 10.1. So I type in 10.1, and there it is, job is finished. That's all it is. It's just looking for you to measure the voltage going out to your system, and then enter it in to make sure that this is just a test to make sure that the system is actually sending the appropriate amount of voltage out to those two terminals. The next thing we're going to want to check is the encoders on our servo motors. So what we're going to do is we're going to go ahead and power down the board. I'm going to hit an E-stop first, powering it down, and then I'm going to actually shut the power off. Because I do not ever want to connect anything to my board while there's any electricity running to any portion of it at any time. So now we're going to grab our spindle and our servo cables. This will be X. I'm just going to plug it in. I'm not going to screw them in. I'm just going to plug them in with number 2. Plug it in. You'll notice we're leaving the power wires unconnected at this time. We're not sending any electricity to the servo motor itself. we're only sending power and receiving signals from the encoder. Okay, we have now plugged in our X, Y, and Z into 1, 2, and 3 on the encoders. After having plugged these in, we are now ready to repower our system. Okay, now that we have the encoders plugged into the board, 1, 2, and 3, being X, Y, and Z, we're going to go ahead and test them in our system. We do this simply first off by touching Setup, going to Configure, typing in our password, and then going to PID. Now, as we turn each of these motors, if you look at the absolute position and the DRO, they both are registering for this axis. So we're going to turn that pretty close to 0. We're going to just do a real quick test on Y. Same thing. Turn it back to 0 or close to it. And then we'll go ahead and do the same thing to the X-axis. Okay? So this is X, Y, and Z, and you can see absolute position is showing readings, and so is the DROs. Now, the DROs is showing how many inches it thinks it's moving. The absolute position is showing how many counts of the encoder is receiving. Remember, we told it that we said there are 8,000 steps per revolution on our encoder. The absolute position refers to how many steps the encoder is receiving as an input signal. So we're going to test it really quick, like by just taking each of the motors, kind of knowing where the key shaft is, and just do one complete revolution on it, and then looking at our screen and making sure that it's 8,000 or really close to it. And that one is. So we'll do the same here. We'll spin this one around, just about one turn, and there's 8,000 again, and we'll do it one more time for the X-axis. We'll spin it around one revolution, and it's pretty close to 8,000. Again, this isn't precise positioning. What we're doing is checking to make sure that all these are what we have configured them to be. And so far, everything is. So far, we're doing great. Okay, we have completed all the software testing that we can do for the bench testing of this system. Any further testing will actually have to be done on the machine. I'll wire in the home and limit switches, bring in the power for the VFD, and set it all up inside of there. We will then go ahead and move on and mount the motors to where they belong, and then wire them into our board. Let's talk about limit switches for just a moment. Now, on my machine, the limit switches for Z are functioning. They both work perfectly, just exactly the way they should. The X and Y axes on this machine, I only have one limit switch per axis. Ajax CNC needs to see two separate individual signals for home and for limit. So instead of knowing which direction it was going when it impacted the switch and then being able to utilize that switch for either X positive or X negative limit, it needs a separate signal and a separate switch apparently for each of those movements. The X-axis travel switch on my machine functions intermittently. It's not reliable, and it does not respond properly. So what I have done is I have disabled them on the board here, and I've pulled the dip switches up for those two, for X and Y, and I have let Z alone. Now I've brought Z in here and here. Now you'll notice I went ahead and run the wires for my X and Y positive and negative movement here and here. But currently they are not wired to anything. That's because I'm going to have to rework those switches and redesign how they function a little bit so that I can put them on there and get both positive and negative separate signals. That does not mean I'm running without any kind of limiting on the system. There is a different way to home it, and there's a different way to run limits. So currently what I'm running is software limits on the table. Now you have to be careful with that due to errors. Things can happen. You can exceed and go too far. It's not a long-term solution. I need to get my machine up and running and making parts. So for me, it's a short-term solution. I will go ahead and build those limit switches and put them together and put them on there. And then once I do, as you can see, everything's already pre-wired for it. I won't have to go into anything extraordinary in order to bring those wires in. to begin the motor installation portion of our upgrade now. And let's start with the Z-axis motor. Now when I've got this motor had already been removed, and I believe there's a cover plate that's supposed to go here to cover the belt. It was removed. However, I did have the timing pulley that he had pulled off of there. One note that you need to know, I'll bring this in a little closer. This hole is the right size. However, this keyway initially is not the right size. It has a very small keyway on the original motor, and you will have to rebroach this to the proper size in order to make this work. So, I have already rebroached this. I was fortunate enough that when I got this machine, for some reason or another, he included a $400 broaching kit. Maybe he had purchased it for that purpose. I do not know. I don't care. I did pretty good on that deal. So, this has already been rebroached, but understand you will have to do that. Also, the faceplate of a new NEMA 34 has a slight lip around the face of it here. Anybody that's messed with the NEMA motors knows that that's there. On the other two axes, that will not matter. On this axis, however, the hole in the top plate here is too small to fit that. So until I make an adapter plate, what I have done is purchased four roughly 1/4 inch thick bronze bushings that are slightly thicker than the race portion of that NEMA motor. So we're just going to place them on top of here, and that gives us basically that acts as a standoff. Also, on the face of your NEMA motors, you will need to thread these holes to a 5/16 18 thread. That's the standard size bolt that comes with this. The bolt patterns on mine match up perfectly. I don't have to do anything special, but I do need to thread these. You don't have to drill them out. They're already drilled for that tap. All you have to do is tap them with 5/16 18 threads. So let's go ahead and set this first one in place here. Okay, have the motor set in place. Make sure that our keyway is in our shaft. Now I don't know how this originally came off, so I'm going to put it with the set screw hole towards the top, because I believe with this standoff it lifts the shaft slightly higher than it would normally have been, and we don't want to shorten ourselves on the ability to tighten it up. And I give myself just a little bit of clearance there. Actually helps if you use the right size X key wrench. Okay, that's tightened down. There is something to be said for picking up someone else's project after they've already begun it. And usually that's something that you want to say is something bad. You can't always find all the screws, and you have to redo things. So I'm using different types of screws that were probably originally on this. Same thread and everything, but it's just frustrating when you have to finish somebody else's started project and you come in the middle of the mess, as it were. Well, anyway, we're going to go ahead and get these all set up in here. Now I'm just going to pull this by hand and pull it tight. And that should be enough pressure on that belt to keep it. Okay, that's our Z-axis. Go ahead and take our cable and route it around behind the machine and over the top. We'll put the excess inside the cabinet so that we don't have to look at it or trip over it. So, there's your Z-axis. Let's open this up real quick, Light, so that I can show you what lies behind this. There's only two Allen screws here. that hold this on. He had already apparently begun this process as well. Behind this cover plate, you will see that we've got 3 switches. I'm assuming that this is the panic switch. If it screws up and bypasses this, this was the actual absolute one. It has been currently disabled. These are roller type paddle switches here. And then there is a small bump on this device here that will engage that. So we just wired in this one and this one as our upper and lower limits. That's all you have to do to this. You disable this one completely. I'm going to take care of these 2 motors now. This one is covered by 3 cap screws. We're going to set these up here where I know where I can find them again. Be careful with this. There's a fine-tooth gear in here with an analog counter in here, which is kind of cool. We're gonna reset those and get down to 0 just because, I don't know, they're kind of fun. And this is what it looks like when you open this up. Now, I've never seen a system quite like this, and I was kind of impressed actually. I don't know if you can see this or not. Yes, you can. Again, use the right size. This has set screws in the face of the pulley on either side of it. You just unscrew them. You'll probably have to break them once a little bit, pinch this belt down to keep that hold in place, and unscrew it. Pull them all the way out. Because what this is a split here in this portion of it, and this is a wedged pulley that goes on the inside of this hub. So if you just tap it right now, you can see they come apart. And you can pull out the center of that hub. That center of that hub is tapered slightly, so that it fits into the taper of this pulley. And then those set screws pull those 2 together, jamming that inside the pulley and then closing the gap on this so that it pinches the shaft. So it doesn't actually require a keyway, even though it has one cut in it, because it just wedges itself onto the shaft. So go ahead and remove that. Lift your belt out. Now this has 4 bolts into the face of the step over here. Try to spin them out. And beware, these step motors are pretty heavy. So be ready to catch it. Don't pull all your bolts all the way out. Leave that last one in there a little bit. Go ahead and take out the rest of them. And just slip the motor out. Set it off to the side. Place the keyway. Make sure that you have your keyway in your shaft. Of course, you don't have to do that now, but you could. I'm going to orient mine, making sure that the wires are sticking down from the motor so that they fall naturally. They can either go this way or that way. You don't want to turn them the other way because it'll put an unnatural kink in the wire. We're going to put it down, line up our motor, and thread our first bolt in there. Set these down. Now, before we go too much further, set our belt back on here. Take the large shiny pulley and set it back in here. And then take our shaft wedge and line it up with the keyway on the shaft. There we go. Now all we have to do is really align the holes bolts, like this. Take our set screws. Now I don't want to wedge it on there too tight yet. I'll run it back and forth a little bit until I'm happy that it's straight and not rubbing. We're going to go ahead and pull it down now. Now pinch the belt in order to put the bind on the set screws. Now, gravity is our friend today. We're going to loosen this one back up. So the weight of the motor is down, helping us pull down on it. Just going to push down by hand again, and then tighten that up. The hole on this one, and the hole on this one over here, is actually large enough that that step out that I was talking about on the first motor fits in the hole, so we don't have to have any spacers behind these. This one's a little more difficult. Not a lot, just a little. Because the bolts are behind this here and behind here. Well, these top two are kind of short, a little bit difficult to get a hold of. These bottom two aren't quite so bad, but you'll need a bent collar for that. I'm going to go ahead and sit on the floor in order to be able to get to where I need to be. So I already cheated, and I loosened these top ones up, and I left them just finger tight. So that when I went to do this, it would have been easier, I should say. And there we go. Now, you make sure, once again, that you point your wires down so that you're not putting undue force on them over the years. And have your screws and everything ready so that when you do finally get it fished into place, you can just go ahead and reach for your, and there we go. It's on there. Come up this way here. My first bolt in there.